We have Professor Sol Gruner with us today, who's going to be talking about some of his work on biology. But let me give you a little background on Sol. He got his PhD in Princeton, and immediately after that, he went on the faculty. And he was on the faculty of Princeton University for from 78 to 97, almost 20 years. Is that right? He left Princeton to move up a step, right? He went to Cornell, and he became the director of CHESS, the Cornell High Energy Synchrotron Source, from 1997 until last year when Sol stepped down as the director. He still remains on the faculty at Cornell, but is devoting less of his time to administration, he tells me, and more to the fun stuff in life. Most of us probably know Sol through his work with X-ray detectors, but he also is well known in other communities, the biophysics community, for instance. He has done work on lipid biomembranes. He's done work on polymers. Much of that work has been recognized by him being elected a fellow of both the American Physical Society and AAAS. Sol has volunteered his time to be on a slew of advisory committees, from high-level DOE, NIH, to more local SLAC, Argonne, NSLS, DAISY. I'm sure I missed some facility that you've probably advised over the years. But lately, his interest has been focusing on high-pressure effects on macromolecules, and in fact, that's the title or the theme of his talk today. So I'd like to introduce Sol, and
thank you, Denny. It's a great pleasure to be here on a perfect Chicago weather day. I feel right at home. I understand Ithaca is sitting under 8 to 12 inches, so it makes no difference as it turns out. It's wonderful to be back on the stage and see many friends who I haven't seen in quite some time. What I'd like to talk about is putting the squeeze on biology. And to start with, I'd like to talk a little bit about lampposts. There's a lamppost and people clustered under it, and as scientists, we tend to cluster under lampposts. And what I'd like to tell you about today is something that's outside of the lamppost. Because we always have to remind ourselves that although it may seem like everything that's under the lamppost is all that's going on, in fact, there's a huge world if you look outside of that lamppost. Most of the natural phenomena in our world has not been explored in detail, and in fact is not understood. So this talk is going to be about science not under the lamppost. And I put that forward particularly for students who may be in the audience because there are a lot of things I'm going to describe which you can make careers out of. Let's start. You've had too much to drink. I'm sure this never happens here. And you need to drive home, and you foolishly get into your car and start weaving down the road. And pretty soon you find that another car is pulling up behind you with flashing lights and a siren. What do you do to get out of trouble? Anybody know? This will work. Okay? It turns out, and it's been known since almost 75 years, that high pressure, a couple of 100 atmospheres, will reverse the effect of soporifics and anesthetics. Now, that's very puzzling. Exactly why that's going on at a molecular level is not at all understood. And in fact, you could see cases. That's one. This is bull sperm inside a capillary that's at 1 atmosphere, and we added alcohol, ethanol, at roughly the concentration you would have if you were very drunk. And you notice that there's swimming in there, but that's because those sperm are drunk. Okay, they're not swimming very quickly. Now, if I were to take that same capillary and pressurize it to 1,500 atmospheres, they're much more active. And in fact, you could do this with fish. You could take fish and put them inside an aquarium. Obviously, it's enclosed. And you inject ethanol, and the goldfish would normally swim like this, start swimming like this because they're inebriated. And then you pressurize, and they'll go right up. And then you depressurize, and you're inebriated again. What is going on? Well, It's actually very, very complicated and very, very poorly understood. It turns out that pressure affects many biological systems. And of course, at the organismal level, these are very complicated, but you could see a lot of things happening at the molecular level, which we're particularly more interested in because we could explore them. Pressure unfolds proteins. This was first discovered by Percy Bridgman in 1914. Percy Bridgman is often called the father of high-pressure physics. He invented something called the Bridgman seal, which allowed you to get to tens of kilobar pressures. And one of the first things he did is he took some egg white and put it inside a high-pressure press and squeezed it, and it came out looking like it was hard-boiled. He had denatured the albumin, the egg white protein largely, in the same way that you denature it when you boil it. In fact, if you go to Japan, you could buy eggs that are hard-boiled that have never been heated. They've just been very slowly pressurized through the porous shell. They're expensive, they're a novelty. This is a way that you could also sterilize foods. It's an FDA-approved way. Pressure also will cause multimeric proteins to associate or dissociate, depending on the particular system. It'll cause changes in binding of things to proteins, ligand binding of substrates. It'll alter membrane ion transduction. It'll change the transcription of nucleic acids, cause large shifts in chemical kinetic constants, changes in conformational states, and greatly decrease viral infectivity. The list goes on. And for many of these things, I'm not talking about a few percent change. The viral infectivity is 3 or 4 orders of magnitude change. These are huge changes. Okay, so what is going on? Why are there such big changes? Well, first thing we have to realize is this is science not under the lamppost, but it's not obscure science. You may think that talking about the effect of pressure on proteins is something that only a small number of people look at, and that's true, only a small number of people look at. But it's not because it isn't prevalent. We tend to think, because we live in one atmosphere, that all of life occurs in one atmosphere. That's not true. High pressure in the biosphere is not exceptional. In fact, in many ways, it's the norm. 62% of the biospheric volume is above 100 atmospheres. You get down to the bottom of the ocean trenches, you're above a kilobar. And if you start including, as many people now believe, that there are organisms that exist inside the crust of the Earth, then the volumes and pressures that are involved are enormous. So in some sense, we are the exception. So here you have a phenomena that really on this planet is very, very extensive, been cataloged by many, many biologists, and at the molecular level is basically not understood in almost every case. That's what I mean by science not under the lamppost. This is really puzzling because the materials of which biological substances are made are actually very stiff. You know, we know that water is very stiff. It compresses only about 50 parts per million per atmosphere. And octane, which is just a proxy for the oily substances in our bodies, about twice as compressible. Proteins are really stiff, about 10 parts per million per atmosphere. Proteins have the compressibility of aluminum. Okay, they're really very compact. Okay, so the P delta V work you do when you go to 100 bar or even a kilobar really isn't very much. So why are there big changes in the molecular system? Well, ultimately, to understand that, we have to realize that a macromolecular system has a huge conformational ensemble. And it doesn't take much change to move into a completely different conformational ensemble, much change energy-wise, although it's often a very big change structurally. To do this, I'd like to have a particular example. The example is what I like to call fish trap zyme. Okay? Now, fish trap zyme, and I'll illustrate it because I brought a sample of fish trap zyme with me, is this. You know, Cornell sits on the side of Cayuga Lake. Cayuga Lake is a very deep lake. The bottom is actually below sea level, 500 feet deep. Okay? And we go fishing in Cayuga Lake, but because we're physicists, we have to do things differently. So here's a typical fishing apparatus that we use. This will work. Okay. There's a little worm here. And what you do is you set this. This is a bistable object. You'll notice it has 2 free energy minima, right? As it is right now, we're set. What you do is you lower this into the water, and the fish come, they tug on the little worm, right? And then it goes into the second stable state, which often means a crushed fish. But you've got your fish. Well, what I'm going to do is I'm going to modify this thing, which I'll call fish trapzyme, give it a good biological name, the following way. I'm too lazy to make it, so I'll draw it. So there's fish trapzyme, and I'm going to put an oil-filled piston connected by a string to the trigger. Okay, now as we know, the compressibility of oil is twice that of water. Okay, and I could always make this piston sufficiently long relative to the surface area of the piston so that an arbitrarily small pressure change will cause that piston to move enough to pull on the string and flip that between its two conformational states. Okay? Now it turns out that I can make that piston long enough that at the surface of Cayuga Lake, if it's set into the ready to catch a fish state, it's fine. But if I drop it down to the bottom of Cayuga Lake, 500 feet down, the pressure is sufficiently higher, the piston will have moved, it flips into the second state, and I catch no fish. Okay? It's very clear how this thing works, because we can see structurally how it's put together. But imagine that this were a protein. Okay? You could see the effects. You catch fish at the surface, you don't catch fish at high pressure, and your job is to try to understand why it's not working at high pressure, why its operation has altered. Now, if you try to understand that in a purely thermodynamic sense, you could do measurements. You can notice that delta V over delta P is very small for this object, change in volume pressure. You can notice that trapzyme has dramatic conformational changes. It has two stable states. You may measure the entropy with respect to pressure and find that it's either positive or negative, depends on the materials that it's made of. In this case, it'd be dominated by the compressibility of the wood base. It doesn't give you a lot of insight, but at the same time, you understand what's going on because you can see how the thing is put together, and you can see how the parts interact with one another, and you can immediately grasp that the reason that it doesn't work at the bottom of the lake versus the top of the lake is because there's a differential compressibility of the oil in that piston relative to the water that surrounds it, which allows it to flip between these two conformational states. In other words, you understand the structure well enough and how the parts interact, see how the thing works. And that, in some sense, is the job that we have in front of us to understand a lot of those pressure effects that I listed at the very beginning. Okay, so what I'd like to do now is give you two mini-stories. First one has to do with lipid membrane mesophases. This is a macromolecular system, which, as you will see, exhibits extremely interesting pressure behavior. The reason I'm going to talk about it is because it's, in some sense, a macromolecular system that's sufficiently simple that we could understand how the parts work, how they interact with one another. And then I'll move to the more complicated case of proteins. So let me remind you about lipids. This is a electron micrograph of a rat liver cell, and all this gray stuff, which you probably can't see unless you're sitting in the front row, are actually membranous organelles. Most of us have cells. I think all of us have cells. And those cells are eukaryotes. They have a lot of membranous organelles inside. In fact, roughly 1/3, very roughly, of the dry mass most eukaryotic cells consists of membranes. Now, let's take one of those membranes from one of those organelles, and here's a cartoon of it. Typically, it's a lipid bilayer, a biomolecular sheet of these fatty acid kind of molecules connected to polar head groups with proteins studied in it. Roughly half the mass is lipid and half the mass is the protein. Now, what I'd like to do is take a particular membranous organelle, doesn't matter which one, let's take one of the two membranes that you have in mitochondria, isolate that membrane, and then purify it into separate fractions. And what you find, it's half protein, half lipid. Let me throw the protein away and just focus on the lipid for the moment. Remind you about these lipids. There are thousands upon thousands of different kinds of lipids inside every cell of your body, but they're built on a very, very simple scheme, and although there are variations, the predominant one is based on two fatty acid chains connected to roughly one of a dozen different kind of head groups. So you may have head groups based on molecules such as choline, serine, ethanolamine, and so on, connected by a backbone, usually glycerol-based. Two fatty acid chains, those are simply number of carbon atoms in a row that may vary from a few to, say, 24. You may or may not have double bonds at various places, and if you take that repertoire of parts, a dozen head groups, and that kind of plasticity of chains, by combining them in different ways, you have thousands and thousands of different molecules. Okay, so let's take the outer membrane from an organelle, and let's fractionate the lipids into chemically pure species and take each one of those species Now you have a little bottle, you have just one kind of chemically pure lipid in it. Let me add water to it and see what it does. And very typically, it will form bilamellar sheets, bilayers. Typically, the chains will be melted. That's why it's called the L-alpha. The alpha indicates that these are melted chain phases. Okay, I'm just showing a cross-section for these. They often form concentric onion-like entities of bilayers with water in between. Now, the cartoons we're going to use are standard. Head group's just a dot. Chains are hydrocarbon. They're little squiggly lines. I'll use purple for water. So if you were to take a section through a multilamellar vesicle, you might have a succession of bilayers with water layers in between. The reason the molecules do this is because the head groups are polar. They're typically charged or dipolar. They like to be in water to lower their overall free energy. The chains are fatty acid. They're oily. They want to be out of contact with water. And if you stop and think about it, this is a way that the head group could be in contact with water. The chains are out of contact with water. They're shielded by the two layers of head groups on either side. It's very simple. What you find is if you take a typical lipid system and you heat it, though, it undergoes a phase transition and turns into something else. Because there's more than one way, in fact, there's an infinite number of geometries whereby you can keep the head groups in contact with water, hydrocarbon tails out of contact with water. And here's the most common one that you see, called the inverse hexagonal or H2 phase. What happens, the system will just change its geometry completely. You increase the temperature. And the water will recast itself into tubes of water on a two-dimensional hexagonal lattice. The outside of those water tubes are completely coated with the head groups of the lipid. The hydrocarbon chains splay out and fill out the volume in between. I've drawn circles here just to guide the eye, of course. That's just a pure hydrocarbon matrix in between. So the question that we have to ask is, what is the physics that controls this transition from the L-alpha state to the inverse hexagonal state? Okay? 25 years ago, I spent a lot of time trying to understand the system, and it turns out to have a relatively simple answer. I'll simplify a lot of things, but ultimately what you will find is that the phase transition behavior is controlled by two competing free energy functionals that cannot be simultaneously minimized for a given geometry. I'll explain what I mean by that in a moment. It turns out that those functionals are the curvature elasticity of the monolayers that make up both bilayers in the H2 phase, and something that we call the hydrocarbon chain packing stress. That is to say, the fact that the hydrocarbon chains have a limited range over which they can stretch. Okay, so let me go through these in some detail because eventually I'm going to get back to pressure. This is, in somewhat more detail, a monolayer of lipid. There are the head groups, charged or dipolar. Water is out here. They like to be in contact with water. There are the hydrocarbon chains, oily. They like to be out of contact with water. What sets the distance between two neighboring molecules? Well, it's a function of the minimum in the interaction potential between neighboring molecules. But the kinds of interactions that you have in the head group region, hydrogen bonding, polar interactions, are qualitatively different than what you have down in the hydrocarbon region, where you're dominated primarily by van der Waals forces and steric exclusion. And therefore, the minimum in the interaction potential that you have in the head group region may be different than the minimum in the interaction potential that you have inside the hydrocarbon region. And therefore, the head groups may want to be at a different distance neighboring next to one another than the tails. Okay? And typically, that's the case, unless you're just fortuitously lucky to have the minimum in the interaction potential between those two regions in exactly the same place. When that happens, the monolayers would like to spontaneously curl. The head group seeking the distance between neighboring head groups that they want, the tails likewise. And what you find, this can be characterized by liquid crystal theory, that it bends and forms an object that has a well-defined radius of curvature, which we'll call the spontaneous radius of curvature. Now, the actual radius of curvature you impose is whatever it's physically bent to, and the free energy functional looks like this, that the square of the difference of those two curvatures, curvature being 1 over the radius of curvature in this case, okay, gives you the energy it takes to achieve that particular radius. Notice that if R equals R0, it's elastically relaxed. This quantity is 0. That's a free energy minimum. If R is either larger or smaller than R0, okay, that's not 0. You square it so it's positive, so you're at the bottom of a parabolic well. Okay? Okay. We're all used to spontaneous curvatures, whether you know it or not. Here's an object that we study very intensively, especially in the summertime. And it has a spontaneous radius of curvature. I'll prove to you by cutting out a piece of rubber. Turns out that the spontaneous radius of curvature of a tennis ball is intentionally built in to be the radius of the tennis ball. That way, any deformation of the tennis ball stores energy. So you hit it with a racket, it bounces off. And in fact, the ball goes flat when you've manipulated the rubber long enough to change the spontaneous radius of curvature from the actual radius of curvature, because it no longer bounces as well. Now, the essence of what I'm going to tell you is as follows. If you consider this to be a lipid monolayer, and suppose that that's the spontaneous radius of curvature that it actually wants to be at, let the fuzzy side be the hydrocarbon chains and the rubber side be the head group side. It wants the curl like this to be elastically relaxed. Okay? Elastic, if I do work on it, I'm storing energy in a spring, bounces right back. Now, if I have two of these, and I try to put them in a water environment, I've got a problem. The hydrocarbon chains don't like being in contact with water. So what they normally do is that. You notice that in order to flatten into a bilayer like that, I had to store elastic energy by bending the monolayers against their spontaneous radius of curvature. Really wants to do is that, but it can't do that. Can't do that because these hydrocarbon chains are really very much like a fluid, and the free energy cost of putting voids in the fluid is prohibitive. Okay? So there's this competition inside the system. Elastically, it wants to do that. Shield hydrocarbon chains and keep from having voids in the hydrocarbon fluid, it wants to do that. Elastically, it wants to do that. Whether it stays in the bilayer phase or goes into the inverse hexagonal phase depends on which of the magnitude of those two functionals dominate. It's that simple. So let me take that a step further. Here's the inverse hexagonal phase. There is the annulus of hydrocarbon chains. There's two representative molecules just to guide you. And what I've drawn here is uniform thickness annulus. You'll notice that if you try to pack cylinders, this is a subsection of a hexagonal lattice, you try to pack cylinders, the central region has a problem. The chains have to really stretch, reach into that region. Now, a hydrocarbon chain normally has a lot of what they call Gauss-Rotamers, 3 degrees of freedom that you have around a carbon single bond. And only one of them allows the chain to be straight relative to its neighbor. The two others each are about half kT extra energy. So if you want to straighten the chain, you actually have to feed energy into the system. So it costs to have that triangle there. Now, if you were to shrink the size of the tubes, keeping the annulus thickness the same, to shrink the spontaneous radius of curvature, then the relative volume of that little space compared to the total volume shrinks. In fact, it goes as the first order of the radius. And therefore, this is easier to pack than this. The lesson here is the larger the size of the cylinders, the more difficult hydrocarbon packing problem is. One other thing you need to put it all together, and that is that the number of Gauss-Rotamers you're going to excite in the hydrocarbon chains, which is going to determine how widely splayed the tails of those lipids are, turns out to be a very strong function of temperature because each excitation is about 1/2 kT. Okay, so the upshot of all that is at low temperature you excite, relatively speaking, fewer Gauss-Rotamers in the chains than you do at a high temperature. Alternatively stated, at low temperature you form a time-averaged object, think about it just oscillating and rotating, that tiles a larger cylinder than at high temperature. In other words, raising the temperature moves you from this tile shape to this tile shape, or from this overall object to this overall object. Okay? So I hope you're starting to see the competitions that are involved. Thing wants to elastically relax to whatever spontaneous radius of curvature is set by the temperature and the chemistry of the system. If it forms really big cylinders, it has a big problem filling those holes between the system. Okay? And that mitigates against it forming really, really big cylinders. Okay. I'm going to sum that all up in a few statements. The lamellar to inverse hexagonal transition is dominated by a competition between the monolayer spontaneous curvature and the need to pack the hydrocarbon chains at near constant fluid density, the carbons per unit volume. Larger inverse hexagonal tubes shift the equilibrium towards the lamellar phase because it's harder and harder to pack that region if that triangle gets bigger and bigger and bigger, which is what happens when the cylinder size gets bigger. And monolayer spontaneous curvature is dominated by chain disorder. That disorder increases with temperature. That's just a shorthand for saying that for a typical lipid, increase in temperature decreases the radius, the spontaneous radius of curvature that it will seek. Okay? So you could sum that all up in two statements. Higher temperature pushes the system thermodynamically to have smaller tubes, more stable H2 phases. Now let's see if that actually works. We could take lipid and put it in the bottom of a little glass capillary, put a big plug of water on top of it. The system will expel water into the bulk phase or draw it from the bulk phase. The water is not a constraint. Okay? And then we could shoot X-rays through it, and by analysis of the diffraction pattern, the symmetry of the diffraction pattern will tell us whether we're in the lamellar or the inverse hexagonal phase, and the dimensions of the diffraction pattern will tell us the unit cells that are involved. So we can determine both the phase and the unit cell sizes that are involved. This is what happens when you take this particular lipid. It's called dioleal phosphatidylethanolamine, 18-carbon lipid with two cis double bonds inside number 9 position, commonly called DOP, dioleal phosphatidylethanolamine, which is a good name for it unless you happen to have collaborators in Canada who are sending you this stuff. When we first started these experiments, they're sending us little vials of white powder across the border labeled dope, and that didn't work, we discovered. If you take some of that stuff and stick it inside the capillary with water on top of it and examine the phase behavior, this is what you typically see. I won't go into what happens at cold temperatures, but roughly from freezing to about 6 or 7 degrees, it's in a lamellar phase. Okay? It's illustrated by these squares, and what's shown here is the repeat spacing between adjacent bilayers, from the middle one bilayer to the one on top of it. It'll spontaneously form a lamellar phase with a well-defined D-spacing. Again, I won't go into why it does that, but it does. Above 6 or 7 degrees, it'll spontaneously undergo a first-order phase transition to this inverse hexagonal or H2 phase. And the first thing we notice is striking is you increase the temperature, the size of the H2 phase, that's the distance from the center of one cylinder to the next, falls very dramatically. So it first starts out at 82 or so, 83 angstroms, and by the time you get to 80 degrees, it's down roughly at 65 angstroms. The tubes are shrinking. The reason they're shrinking is because the spontaneous curvature of the lipids are driving them that direction. As the temperature goes up, the chains become more splayed. More splayed forms a molecular object that tiles a smaller cylinder, pushes water out into the bulk phase. Why that big change in radius? Just pure geometry. If we take a section of a bilayer, there are two molecules. The volume per molecule is about 1,250 cubic angstroms. The thickness of this object is about 20 angstroms. And because this is divided into little cubic rectangles, if you will, that tile the whole volume, the area per molecule is about 62.5 angstroms. Now, as you heat the object up or cool it down, you'll change the thickness of this because you introduce more Gauss-Rotamers. That is reflected ultimately in a change in the area. The actual numbers turn out to be this, that if you would change the temperature by 10 or 15 degrees, you might expand the hydrocarbon region by 0.2 of an angstrom. Just go through the math, that changes the area by 61.9 angstroms per molecule. The total change in the bilayer thickness is 0.2 of an angstrom per monolayer. For the H2 phase, we have a different situation. That's because in a lamellar phase, we are constrained to have the volume equal to the thickness times the area. But in a two-dimensional geometry, you have an additional degree of freedom. You could change the area and the thickness of the annulus independent of one another. It's just a consequence of the geometry. So let's go through an H2 phase. Same volume per molecule, 1,250 cubic angstroms. It turns out the area per molecule that we typically see is about 50 square angstroms. Let me change the thickness of the hydrocarbon layer by the same 0.2 of an angstrom. We'll see in a moment. This object will tile a cylinder of radius about 40 angstroms. If I change it by 0.2 of an angstrom, it's reflected in a change of radius of 2.5 angstroms, or a total change in the despacing of 5 angstroms. So that very small change in the thickness of the hydrocarbon, driven by thermal excitations of Gauss-Rotemers, that drives a very slight change in thickness of bilayer, will drive a very large change in the size of the tubes that you have in the H2. Okay, it's just geometry. And if you do that very carefully, it turns out that you could theoretically predict with 0 degrees freedom, okay, with no free parameters, exactly what the system is going to do. Okay, let me get back to pressure. Okay, so what I've done so far is taken you on this diversion where I've explained the physics of a particular phase transitional lipid system. And I hope you can see that the system is dominated by the excitation of Gauss-Rotemers inside this hydrocarbon layer. And ultimately, that's reflected in which of 2 phases the system wants to be by this competition between spontaneous curvature and the necessity of trying to fill the hydrocarbon zone with some hydrocarbon fluid of constant density. Given the temperature dependence, what do you predict about the pressure dependence? What's pressure going to do to the hydrocarbon fluid? One would expect that the effect of pressure is to reduce the overall volume. Since the atoms are hard, how do you reduce the overall volume? You reduce the microscopic fluctuating voids in the system. You do that by reducing the number of Gauss-Rotemers or kinks in the chain, becomes more extended. In other words, raising the pressure is sort of like lowering the temperature. Okay, you iron out a lot of the microscopic voids in the system. But we've already learned that if you make the hydrocarbon chains more straight, you form a molecular object that tiles a larger cylinder. And we've already learned that the larger the size of the cylinder, the more difficult it is to pack hydrocarbon in that little triangle. Okay? So you could control the phase transition by applying pressure and understand the mechanism through which it's operating. It's changing the overall density of voids, if you will, inside the hydrocarbon fluid. So what would you predict? Well, what you'd predict is, paradoxically, if you apply pressure to an H2 phase, the cylinders would get bigger. Right? Think about it. Now, where's that extra volume coming from? Remember, it's able to draw in water from this coexisting bulk phase. The overall volume of the system actually shrinks. Very little bit. But the H2 phase gets bigger. And in fact, when we tried the experiment, that's exactly what we saw. So this is an H2 phase DOPE in excess water, function of pressure, and it has an enormous increase. If you apply pressure, those cylinders get bigger and bigger and bigger. In fact, they get bigger at the rate of 10 angstroms per kilobar. That's really enormous. Furthermore, remember we said that as the cylinders get bigger and bigger and bigger, it's harder and harder and harder to fill that triangle. So if the phase transition from the lamellar phase to the inverse hexagonal phase is a function of temperature, at higher pressure, you'd expect you have to go to higher temperature to compensate. As to say, the pressure wants to make the cylinders bigger, you have to apply higher temperatures to make them smaller again to affect the phase transition. So you would expect the phase transition from lamellar to inverse hexagonal to climb very, very rapidly with pressure. And when you do the experiment, that's exactly what you see. In fact, this is the most pressure-sensitive condensed matter, non-gaseous phase transition known. And you see that there's your phase transition at 1 atmosphere, 6 or 7 degrees. By the time you get up to 1,500 atmospheres, you've pushed the phase transition from lamellar to hexagonal all the way up to about 65 degrees centigrade. Enormous change. Why am I telling you about this? Well, I'm telling you about this because this is, again, a macromolecular system where you can see how the parts interact with one another. You can understand in very fundamental terms why the system does what it does, exactly as you can understand in fundamental terms why fish trap zyme does not catch fish at the bottom of Cayuga Lake. And by the way, this also works at negative pressure. I think this was the only experiment that's ever been done with liquid crystals at negative pressure. Don't have time to go through it, but if you're interested, remind me afterwards and we can go through it. Okay, so what have we learned so far? Well, we've learned that macromolecules have parts. In the case of the lipid system, those parts are the head groups, the chains, and the water. And we've learned that these parts are subject to many interactions which may be qualitatively different from one part to the next. The head groups may be subject to polar type interactions, hydrogen bonds, and so on. There are other interactions which other parts may have to different degrees. Bond rotation, gauche to trans rotamers, for example, between carbon-carbon bonds, charge, so on and so forth. We've learned that these interactions are pressure sensitive. Okay, it turns out that the head groups are very incompressible with respect to pressure. They don't squeeze together very much when you pressurize them. But the hydrocarbon chains are very compressible in a relative sense. Okay, their compressibility is short of 100 parts per million per atmosphere. So the interactions are pressure sensitive. That's to say, one part of the structure may compress at a different rate than another part of the structure. And if the differential compressibilities are coupled to what the system will do, as I just showed you in the case of lamellar inverse hexagonal phases, then you could see how small changes in relative volume, the differential compressibility, can actually cause the system to do something quite dramatic, like go from lamellae to inverse hexagonal tubes. An alternative language is to say that macromolecules have many conformations, and the ensemble of conformational states can be shifted by subtle changes in pressure. What about proteins? Well, proteins have parts too. Typical protein will have alpha helices, beta sheets, water, tertiary and quaternary domains. It also has a very large ensemble of conformations. And the functionality of a typical protein, an enzyme, is very much a strong function of the way this conformational ensemble maneuvers the parts relative to one another to perform a given function. Protein function depends on the conformations, which we all know, which depends in terms of the relative positions of residues in larger parts. And therefore, if by applying pressure we cause one part of the protein, say the alpha helical region, to have a very different compressibility than another part of the protein, we can cause subtle shifts, and those subtle shifts can have big effects on what the protein is going to do. So I remind you, for example, in the hemoglobin or myoglobin, the oxygen-binding proteins, when you bind oxygen, there's a porphyrin ring, bind the oxygen too. That puckers by a few tenths of an angstrom. It's a very small change, but if you affect that, it turns out to be very pressure sensitive. You can control what that molecule will do with respect to binding of oxygen. Let me remind you again, this audience probably doesn't need reminding, that structural information is important, okay? And that if you look at a blob of atoms, it often doesn't give you the information of the underlying structure, which would be represented as a ribbon of the primary chain. Same molecule happens to be molecule. So if we really want to understand why it is that pressure has a huge effect on many, many protein systems, and there are literally hundreds, if not thousands, of protein systems have been cataloged, not understood, mind you, but cataloged, having big pressure effects. We want to understand how the structure changes in subtle ways when we apply pressure. Makes sense, right? This is science not in a lamppost. Why don't we do protein crystallography at high pressure? Well, we asked ourselves that question. By 2002, that's when we started working on this. And turns out there are thousands of protein structures. How many do you think have been done at a kilobar or greater? I hear 0. You're close. There was one, okay? And it turns out that one was done by Kundrat and Richards in Yale back in 1987. It was a beautiful experiment. They took a beryllium rod and they drilled a hole in, a dead-ended hole. They put the crystal inside mother liquor in there and they pressurized that beryllium rod and did crystallography right through the wall of the rod. It's about a 1/4 inch in diameter. Difficult experiment because you have all the powder pattern of beryllium in the way, but you could get structure out of it. And they investigated what happened, and they used hen egg white lysozyme. They went up to a kilobar. They found that the isothermal compressibility, well, there's your 5 parts per million per atmosphere. They found the contractions non-uniform. Now, protein crystals under pressure are really different than other kinds of crystals under pressure because a protein crystal is riddled with water channels. That water is fluid, and when you apply pressure to a protein crystal, you are not like a normal organic crystal applying pressure to the faces of the crystal and have a strain gradient across the crystal. Because you have fluid channels permeating, the water transmits the pressure without drop to each protein. There's no pressure gradient across a protein crystal under pressure. Okay? So if the molecule is going to change its shape as a function of the application of pressure, it's free to do so. And since the forces holding the proteins together in the protein crystal are very soft, the crystal simply changes shape, follows suit. Really quite different than things that we're used to inside the normal condensed matter situation. They found the contractions not uniform. The A and B axes contracted by about 0.6% in a kilobar, and the C axis expanded by 0.1%. And that's typical of the kinds of changes you would see. The B factors were very non-uniform, indicating that there are whole regions of the protein that were more compressible than other regions. Exactly what we want to see if we understand differential compressibility as driving the functionality changes we see in proteins. And other than that, they saw overall structural changes very little. Now, this was a tour de force experiment whose impact was completely lost on the community. People looked at this and they said, A and B axes changed by 0.6% and the other one changed by 0.1%. That's insignificant. Okay, and the biologists completely discounted. That's not correct. Remember, when you bind oxygen to that porphyrin ring in hemoglobin, you have a few tenths of an angstrom change. Small changes in the right place are very significant in terms of what that protein is supposed to do. And in fact, in most proteins, enzymes that have an active site, upon actuality, upon functionality, the changes that are initially happening when you bind substrate into the active site are really small, a few tenths of an angstrom. Okay? And if you can shift that few tenths of an angstrom by 2 or 3 tenths of an angstrom, you could really change what that enzyme does. Okay? So this is actually very significant. We borrowed, Fred Richards was kind enough to show us, pass us his beryllium cell. We modified it so we can go to 2 kilobar. We also developed another method, which I won't talk about here, called high-pressure cryocooling, modification of something that was published by Mossbauer and Tomanek, actually back in 1973. You take the crystal, you pressurize it to high pressure at room temperature, and then once it's at a high pressure, we often go to 2 kilobar, you drop the temperature to liquid nitrogen temperature. Turns out that any small changes get frozen in because you get below the glass transition of both the protein and the water, so you can lock in the changes. That's convenient because we're all used to using protein crystallography at cryo beamlines. Okay? You could just take that crystal, always keep it at liquid nitrogen temperature, and run it at your normal beamline and see the changes that happened pressurized at room temperature. Turns out there's some other subtle changes that happen when you change the temperature, but you could unravel them. Turns out also that this methodology is much richer than you might think. There's a reference there if you want to find out more about it. Okay, let me tell you about 2 case examples, things that we've studied, where what we're trying to do is understand how the differential compressibility of the parts of the protein get translated to something that plausibly can be understood as a functional change of significance. Remember I said that enzymes can change their reactivity by orders of magnitude upon application of a few hundred atmospheres of pressure. Can we understand that in terms of changes within the protein which cause small-scale modifications of critical parts of the system? And we searched around and came up with one system that just turned out to be perfect for it. This was the thesis of Buzz Barstow, who's now at Harvard. And we used a protein called citrin. Now, citrin is a mutant analog of green fluorescent protein. I remind you that green fluorescent protein is a protein that is very much beloved by the biological community because you could put this inside a genetic sequence. It gets expressed as a protein just hanging off the edge of protein genome that you've just expressed, and it will glow, it will fluoresce if you hit it with ultraviolet light. Typically, it glows green. Okay? Citrin, which is a mutant, will actually glow towards lemon yellow. That's why it's called citrin. Now, if you look at green fluorescent protein, the thing that makes it glow, the chromophore, is this group. It's a modified amino acid. In citrin, there's yet another amino acid, a tyrosine, which sits on top of it. Okay? And the thing that Buzz noticed when I said, find a system where we could probe it optically so we could do optical experiments and pressure bombs and also probe it structurally, he came up with this one. Turns out that here's citrin's excitation, and there's the emission spectrum. Okay? And what he particularly noted was the following. Lost my point. He noticed that in the literature, people had cataloged how the peak fluorescence shifts as a function of pressure. For green fluorescent protein, for which there's only one chromophore, you don't have that tyrosine sitting on top of it, there is no shift, zero, inside the peak fluorescent function pressure. But in citrin, there is. And that immediately rang bells in our head, because we know whenever you have two aromatic systems that are sitting on top of one another, there's pi bonding between the aromatic rings, and we know that that's an energy transfer, and we know that that will affect the fluorescence, and we know that a few tenths of an angstrom shift of one aromatic ring with respect to the other can really cause that peak, the energy transfer, to move all over the place. Okay? So this was an ideal mimic of what happens inside an enzyme system where you have an active site. If we can show that as you pressurize, there's an overall conformational change of the protein, it slowly and smoothly changes its shape, okay, and that affects the spacing between the tyrosine sitting on top of the chromophore, that this is a sort of proof in principle of exactly what's going to be happening inside an enzyme, where you're affecting the geometry of the active site, if the magnitudes of the shift are in the 0.2 to 0.5 of an angstrom. I think I ran out of batteries. What's going on? Whoops. So we did the experiment. If you hold that tyrosine fixed and look at how the chromophore changes as a function of pressure, this is what you see. By the time you go from 1 atmosphere to 4 kilobar, you have a change of almost 0.8, 0.9 of an angstrom shift of one with respect to the other. In fact, if you looked at it from the side, it tilts a little bit, it shifts sideways, and it separates. Easily, large enough magnitude changes to account for the spectral shift that we see. And if you had shifts of this magnitude going on around the, for example, binding site of oxygen inside a heme protein, you would completely change the way that system is. So how are these shifts reflected in the rest of the protein? Well, Buzz analyzed that. Turns out that you could imagine putting axes on this protein and look at the angular deviation of one axis with respect to the other as a function of pressure, and smooth change. It's the composite of a lot of effects that pressure are causing on the system. Ironing out microvoids throughout the protein, it's changing the degree to which water hydrates groups listed. They're all pressure sensitive. And the ensemble of that is to shift the conformational average quite substantially. And in fact, if you model the system as a beta barrel, what you find is that you could resolve parts of the protein into two regions, here coded red and blue. And as you pressurize, the red and blue sort of move independently of one another. In fact, this is an easier way to look at it. This is what citrin looks like. It's a beta barrel, and then there's this primary chain that threads through the middle of the barrel that carries the chromophore, and the tyrosine's hanging off the side of the barrel. And when you pressurize, what happens is this part of the barrel shrinks just a little bit. This part actually expands. And that torques these two aromatic rings apart by exactly the amounts that I showed you. Okay? So again, in a very straightforward, fundamental way, we could understand how pressure is affecting the active site, if you will, of this protein system. And now you go back and say, well, is it surprising that enzymes are very pressure sensitive? The answer is no. If all proteins tend to have these kind of magnitudes of shift, and they do, we've looked at a large number of them, then in fact you'd expect the norm would be that active sites that depend on residues that are not covalently bound to one another locally would be very pressure dependent. Let me give you a second story just to drive that point home. And this is a case of sperm whale myoglobin. It was done by Paul Uriyama, students now in the physics department at Miami University. And we wanted to understand how pressure affects this. Now, we were aided in doing this by the fact that Fraunfelder group at the University of Illinois had done tons of work on this spectroscopically, and we were able to build on that. Let me remind you, sperm whale myoglobin is the first protein structure to have been solved. Andrew solved it, what, 57 or something like that? Won the Nobel Prize for it. 153 amino acids, often called the hydrogen atom of structural biology. The linear polymer folds into 8 alpha helices, as you see here. It has a heme group, this, iron tetracoordinated to a porphyrin ring, and oxygen can bind there. It's involved in oxygen transport. As we now know, it also has functional involvement with NO and CO. Carbon monoxide binds there. Very hard to get out. That's why you suffocate carbon monoxide. Very important protein. It's long been known that there are many, but there are two particular conformational substates, dips in the overall free energy as a function of some reaction coordinate, which are labeled in literature A0 and A1, okay? And they have to do with a histidine that's around that porphyrin site, whether it's in one position or another, very much like the mousetrap, actually. You could vary the conditions of the protein and measure, I'll tell you how you do that in a second, what fraction of the protein is in the A0 conformational state, and what fraction are in the A1 conformational state. And as you vary conditions, and conditions would be pressure, temperature, or pH, you could change the ratio of the number of proteins in a given sample of myoglobin in solution that are in the A0 conformational substate versus the A1. Well, how do you know which one it's in? Turns out that if you bind carbon monoxide into the binding site of myoglobin, there's a certain infrared stretch frequency which is characteristic of the A0 conformational substate, and another frequency of the A1. So you could just do infrared spectroscopy, and by looking at the intensity of these two conformational stretch signals, determine what fraction of the molecules are in one conformational state versus another. So here's work that was done by the Frauenfelder group. There's a lot of information here. Let me walk you through it. There's the molecule. There's that little histidine that controls what's going on, and its position is involved in the A0 and the A1 conformational states. It's connected to the rest of the protein, as is the porphyrin. This is a global conformational state, as they call it. What's shown here is the ratio, the fraction of a given sample that will be in the A0 conformational state relative to the A1 conformational state as a function of different things. A function of temperature, as a function of pH, that's red versus blue, as a function of pressure, that's squares versus circles. Okay, so let's walk through this. First of all, you'll notice that if I look at pH, I remind you again, red is pH 6, high pH, blue is pH 5.5, low pH. You'll notice that red is always below blue. In other words, the higher pH always has more A0 relative to A1 conformational state. We can code that saying as the pH goes down, the number of the A0 conformational substate goes up, the fraction of the system of that goes up. The next thing you notice is that pressure has an effect, squares versus circles. So the circles are atmospheric pressure. Squares, the two pHs are at 200 megapascals, 2 kilobar. And you'll notice that the squares are always above the circles, no matter what the pH. In other words, as the pH is going up, the conformational substate A0 is favored. Finally, you'll notice that as you increase the temperature, all of these curves tend to trend down. Another way of saying that as the temperature goes down, fraction of the system, the A0 conformational substate, goes up. Okay? Now, if the conformational substate is a reflection of a large number of changes throughout the volume of the protein that wind up ultimately determining what's happening around the active site, what you can see right away is that there are many ways to get there. You could change the pH, change the temperature, you could change the pressure, or you could change any combination of the three. What happens is a complicated set of interactions throughout the volume of the protein, which ultimately is reflected in the part of the protein that's doing the real work, the binding of oxygen near the porphyrin site. So we analyzed what happens to the structure of the protein as you change the temperature, the pH, pressure. This is what happened. This is all in the literature. If you want to look up the details, let me just give you the bottom line. Ooh. This is myoglobin viewed from two orthogonal directions for a pH comparison or a pressure comparison. And we've used a trick that's often used in structural biology of amplifying changes by certain factors so they're easier to see. Let's look at the pH comparison to start with. The cyan color is the low pH, and the other color that you see is going to be the higher pH position, the yellow ribbon. And you can see their changes. They're subtle, but they're there. Okay, they're very reproducible and they're well outside of noise. If you look at what happens if you just change the pressure, same thing. Okay. What again we're showing is that at ambient pressure, the yellow ribbon, at high pressure, the green ribbon, again you see changes. And you have to really stare at these things, rotate them in all directions. But if you do that long enough, what you start to notice is the following. That as you change the pH, pressure, or the temperature, and you look at a given ratio of conformations, A0 to A1, that as you approach a given fiducial value of that ratio, changes tend to be very similar around the active site. There are various ways to get there. You can change the pH, the temperature, or the pressure. But at the active site, the part that's important, they're all reflected in a very similar way. And it turns out that the net effect, basically you take this part of the protein to move in that direction, and this alpha helix slides down that way. And that tends to torque on this histidine and causes all the changes. Very complicated system, but in principle, very simple to understand. You can see how the protein is not only sensitive to pressure, but you start to understand why it's pH sensitive, why it's temperature sensitive. Okay, let me summarize because I'm going on too long perhaps. You look at these, you start to really get the picture. The proteins are nano machines, they're nano engines. They've got all kinds of complicated parts, but there's a little working zone typically that turns out to be very important in many proteins. The proteins are truly nanomachines built of interlinked parts, and that's the critical thing. The movement of the parts can be achieved by any kind, lots of different kinds of environmental variables, pressure, pH, and temperature. However, those movements often couple to function in very sensitive active sites. So if you're going to try to understand how it is that the functionality of a protein, which depends on an active site, is dependent on environmental variables, what you really want to do is you want to gauge and carefully watch how the whole protein deforms as you apply your environmental variable and see how those changes are translated into structural changes at the active site. In other words, movements couple to function. That should be no surprise, but it's really not investigated in this very direct way in many, many systems. Pressure, as well as pH and temperature, can be understood in a very unified, intellectually pleasing way. And I hope that you at least see the overall picture of what I'm trying to get at. Okay, so we started this by saying that there are hosts of molecular systems out there been cataloged as being very pressure sensitive. I hope you could see, at least in principle, that you could understand what those changes, how those changes work. You do a detailed analysis of the structure of the molecule and try to understand how the pressure affects those structural changes. I've been really fortunate to work with some really great students and colleagues. That these are a list of ones that have been involved in these pressure studies, which have gone on now for 15 or so years. And I'm always grateful to receive money, and I've been very happy to accept money from a reasonably large number of sources. And I want to thank you for your time and attention.
Well, we have time for a few questions.
Hi, Saul, great talk. I'm going to ask maybe a pedestrian question, but I think might be very interesting to this community, which is, what is the effect of pressure on beam damage, the X-ray beam damage? I could guess it would be much less sensitive at high pressure, but I don't know what...
That's a great question, and I don't know the answer.
Oh, really?
No, we've actually never looked at it.
Oh, because usually you get gas coming off, and that's a change in volume, so I'd assume that the higher pressure would maybe substantially reduce the amount.
As I said, that's a great question. I can't give you an answer. My guess would be that you would reduce the migration of free radicals somewhat, and concomitantly you'd see some reduction in the sensitivity, at least at room temperature, protein with respect to pressure, but I have never looked. You ought to look.
Ergen, go ahead.
Yeah, thank you for a great talk, actually. You're right that we like to stay under the lamppost. We don't like to go too far away from the
We're
lamppost.
human.
And even if you go out the large world, you still have, if you find an interesting problem, you still have to bring it under the lamppost.
Sure.
And I have a comment and a question, actually. We have here a technique called nuclear resonant vibrational spectroscopy to look at those vibrations in porphyrins, for example. So I would like to invite you to actually consider that as a technique of your choice, because it is far more sensitive than the structural probes that one tend to use. And you can have direct access to the central motions of the active site in this method. My question is, have you also considered looking at the density functional theory to see some of the effects you are seeing can be predicted? And have you coupled your studies into some of the modern computational methods?
Yes. We started working with Garrett Hummer, in fact, on the myoglobin system and the citrin system both. We haven't pushed it too far, okay, and we did write a paper on it. We haven't pushed it too far, largely because it's just a question of where one's interests lie. As a physicist, I'm more interested in understanding basic principles than any given protein system. I suppose if I were particularly committed to understanding a protein system, which is often the case, has to be the case, then I would throw every tool I had at it. As it is, I want to understand in an overall sense how it is that pressure affects global conformational change and how that might be coupled active site changes, which is exactly what we do. Your comment about the lamppost, of course, is extremely well taken. What I love to do is to say, well, once you start thinking along these lines, you could very quickly suggest to graduate students experiments that are just itching to be done, okay, which will win you 2 or 3 Nobel Prizes, well, maybe not, win you a lot of acclaim if you only do them, and are perfectly doable. So let me throw it out, an experiment that's never been done, okay, that I think would shed a tremendous amount of light on a particular system. There are various Japanese groups that have analyzed the enzymes in the citric acid cycle used to provide energy to cells, for organisms that exist at the bottom of the Marianas and Japan Trench. And they find that there are a number of very fundamental enzymes in the citric acid cycle that are very pressure dependent. They find these because these bacterial organisms that are habituated to live at the bottom of these ocean trenches tend to grow very, very slowly when they're brought to the surface, and they realize that the reason is because these enzymes don't function very well. These enzymes, of course, have exact analogs to related organisms at the surface, and these surface organisms function poorly when you pressurize them. Okay. The vectors for the genetic sequences for these proteins, which are single-stranded amino acid proteins, are known. You could look them up. You could go into the laboratory and create the vector and express it in E. coli and have tons of both the surface protein and the protein that you can get at the bottom of the trench. Now, if you were then to crystallize those 2 proteins, suppose you choose a particular enzyme in the citric acid cycle, you crystallize one that comes from a genetic sequence of the organisms at the bottom of the ocean compared to the one at the top, you see the kinds of structural changes reflected in an active site that you expect. In particular, when you pressurize the one at the surface, does the active site change relative to the one that you have at the bottom? And in particular, for the different genetic sequences, sequences, the one at the bottom and the top, are they adapted in such a way that at their respective pressures, the active site looks the same? It's a beautiful experiment. It's completely doable, okay? It doesn't require any great amount of new kinds of things that need to be developed. Of course, you have to be able to do the crystallography at high pressure, but a number of places can do it. So there it is. If somebody wants to take that experiment, make a career out of it, believe me, there's a lot there.
You just answered my question. Andy?
Are you going to do the experiment?
Years ago, how sensitive are those transition temperatures to the exact makeup of the hydrocarbon portion? So, for example, if you went to POPC instead of DOPE, are you going to see a very different transition temperature and a different kind of pressure dependence?
Yes.
Okay.
And it's very systematic. So if you were to examine what happens as a function of changing the length of the chain or moving the double bond systematically to the
Right.
middle, it all moves in a very systematic way, but it's very sensitive in that. Okay. And you live because you rely on
Right.
that. Okay, you might recall that when you adapt to this wonderful weather that you have outside versus what you have outside here in August, you change the lipid composition,
Right.
you change the chain composition of many of your membranes, and this is part of the adaptation.
Right. So my question about the second half of your talk, or your second example, you're suggesting that the nature of the changes in myoglobin when you change pressure or temperature are similar to the ones that occur when you change pH, in that they involve global movement of the entire polypeptide, right?
That's correct.
So if I remember the two pH values you were talking about, they're on either sides of the pKa of that histidine. So a simple-minded biochemist like me would wonder whether that could be explained in a much more local way. And so in the sense that, you know, the protonation or deprotonation of that histidine imidazole ring is clearly going to have a very local effect. So I guess the question is,
I will return, Andy, with the question to you.
sure.
How pressure sensitive is that deprotonization?
Ah, okay, that makes sense. So has that been measured?
It has, and in fact, there is some sensitivity to it. But more importantly, you could compensate at one pH and make it behave like it does at the other pH by changing the pressure.
I see. That makes sense. Thanks.
Yeah, so what about some, here.
Okay.
I mean, there's a whole bunch of other parameters you can change, like, say, electric fields or all kinds of ion concentrations, potassium or whatnot, which would also have differential effects on different parts of your proteins. Have you looked at those?
No, my limit is 3. And for a physicist, by the way, that's too many. Not that the other ones don't affect it, not that they're not important, but you know, that's as far as we've gone.
Any other questions? All right, well, let's thank Sol one more time for a very entertaining presentation.